Okay, we're starting a new unit, and the unit is called stoichiometry. So stoichiometry, metry means a measurement, and stoich is a Greek prefix that comes from the word element. So stoichiometry, we're going to measure the elements. We're measuring how many reactants we need to make products, or if we have the amount of products, how many reactants did we start with. So we're taking together Unit 1 and Unit 2, balancing chemical equations, and going from moles to grams, grams to moles, and we're making it into one big unit called stoichiometry. And the way we're going to start is we're going to start with molar ratios. So take a minute to read this first paragraph. When you're done, resume the video. And this paragraph is telling you about molar ratios. So molar ratios are going to be our coefficients. So our coefficients tell us how many moles need to react with each other in order to make a certain amount of products. And we can relate this to like a recipe. So a recipe to make 24 cookies, for every 1 cup of sugar, you need 3 cups of flour. And this is your ratio. And if we wanted to alter the recipe and not make 24 cookies, but make 30 cookies, 8 cookies, it doesn't matter, we know that our ratio of sugar to flour has to stay the same, or else the cookie recipe will not be the same. So what you do is you just do a bunch of ratios to figure out how are you going to alter it. So for example, I'm asking if I only had 1 egg in the fridge, how would I alter the sugar and the flour to make sure that everything turns out okay? And this is an example of using dimensional analysis to try to alter your recipe in order to still get the desired product, even if you don't have enough, or if you have excess, you want to make more. The same thing can be said about a chemical reaction. This balanced chemical equation is like your recipe. You have to follow the recipe and those ratios in order to make the products. The coefficients that are out in front, we're now going to call them molar ratios. They represent how many moles of each thing are reacting. And when we use those moles, we can convert them to mass, so we can figure out what mass of each thing is reacting. This is really important to convert it to mass because we can't weigh out moles on a scale. We can only weigh out grams. So to get them from moles to grams, we're able to actually do it in real life. We don't have to just think about it. We can do it in the lab. And once you convert it from moles to grams, you notice that the law of conservation of mass is conserved. Each side has the same mass. But notice how each side doesn't necessarily have the same amount of moles. How can you have the same mass but not have the same amount of moles? Well, these different compounds weigh differently. Carbon dioxide has a different molar mass than oxygen. So even though I only have 3 carbon dioxides and 5 oxygens, and my product side maybe has a total of 7, 3 plus 4 is 7 reactants, and my reactant side has a total of 6, 1 plus 5 equals 6 reactants. 7 and 6 aren't equivalent to each other, but their relative molar masses will make the masses equivalent to each other. So if you figure out the molar mass of how many moles of each compound you have and you add it up to each side, you will get the mass of each side, the reactants and the products. And it's going to be the same. It must be the same, or else we're not obeying the law of conservation of mass. So let's do some sample problems. So we're going to start with just simple molar ratios. We're going to take the chemical equation that's balanced, and we're going to assign them as molar ratios. So for example, a very simple synthesis reaction of hydrogen and oxygen to make water. So for every 2 moles of hydrogen, I need 1 mole of oxygen to produce 2 moles of water. So now this is our molar ratio. We use these values as our guide to figuring out how we can alter the recipe. So for example, if I want to burn 5 moles of oxygen, how many moles of hydrogen gas is needed? So I start with my 5 moles of oxygen, and my ratio is for every 1 mole of oxygen, I need 2 moles of hydrogen. So I put my unit that I want to get rid of on my denominator. So for every 1 mole of oxygen, and to complete the ratio, I look back at my balanced chemical equation. I need 2 moles of hydrogen. So now, my moles of oxygen will cancel, and the unit you're left over with is moles of hydrogen. In stoichiometry, it is incredibly important that you put both the unit and the identity of each compound or each element, because we're going to start throwing around different units, throwing around different elements, all in one long dimensional analysis, or one long factor labeling. So here, I need 10 moles of hydrogen if I want to use up 5 moles of oxygen to make the same product. So let's practice. All you're going to do is look at these coefficients and plug them in as molar ratios. So for example, this hydrocarbon, butane, has 2 as its coefficient, and oxygen has 13. So the molar ratio that I want you to write to the side is for every 2 moles of butane, you get 13 moles of oxygen, and that's your molar ratio. Same thing for oxygen. You get 13 oxygens here, and for carbon dioxide, 8. I want you to write the ratio in terms of molar ratios. For every 13 moles of oxygen, you get 8 moles of CO2. So go ahead and pause the video and complete the rest of this page, and then I will put up the answers in just a minute. Okay, so hopefully your answers look like mine. I'll just slowly scan through the page, and you can always replay this video if you need to double check your work. But make sure that your molar conversions have the units of moles and identity in your molar ratio. Let's go on to the next page. So on this next page, we're actually going to apply it to a chemical equation. And I want you to start by writing all the possible molar ratios and then choosing which one you need to use in order to solve the problem. So for here, I have the synthesis of ammonia. So it says, what is the molar ratio of all the reactants and products? So first we need to make sure that my chemical equation is balanced. If it's not balanced, then my molar ratios are not going to be correct. So looking here, it looks like I have 2 nitrogens, 2 nitrogens, 6 hydrogens, and 6 hydrogens, so it's balanced. So for every 1 mole of nitrogen, I need 3 moles of hydrogen to react. For every 3 moles of hydrogen, I will produce 2 moles of ammonia. And for every 1 mole of nitrogen, I will produce 2 moles of ammonia. So remember, just like anything in dimensional analysis, you don't have to keep the fractions the way they are looking. You can flip it according to whatever purpose you need it to serve. If you need to cancel out the units, flip it so that way you can cancel out the correct units. So for example, it's 1 mole. If I need 1 mole of nitrogen to react with 3 moles of hydrogen, it's the same thing as saying I need 3 moles of hydrogen to react with 1 mole of nitrogen. And you can do that for every ratio. You can flip it according to what you need to do for the math. Okay? And then we can pick and choose which one we need to solve each question. So, let's look at the first question. It says, if 10 moles of ammonia were produced, how many moles of nitrogen would be required? So I'm going to underline what they're giving me. They're giving me 10 moles of ammonia. I'm going to put a question mark with what I'm trying to solve. So if they're giving me 10 moles of ammonia, they say how many moles of nitrogen would be required. So this is the value I need to get, and this is the value I'm starting with. So you always want to write first what you're given. If you're given 10 moles of ammonia, look for the ratio that you wrote. Where will there be ammonia on the bottom to cancel, and then your moles of nitrogen on the top to solve the problem? This one. There's moles of nitrogen on the bottom to cancel, so I'll put 2 moles of nitrogen down here. Sorry, ammonia. I apologize. And then what I'm looking for is moles of ammonia, moles of nitrogen. So here, my moles of nitrogen are going to cancel, moles of ammonia are going to cancel, and what I'm left over with is moles of nitrogen. So you're going to make 5 moles of nitrogen to make 10 moles of ammonia. Let's do one more. It says, if 0.3 moles of hydrogen were used, so that's what they're giving us, 0.3 moles of hydrogen, how many moles of ammonia would be made? So we're starting with that 0.3 moles of hydrogen, so you got to write down what they give you. And you go, okay, I don't want moles of hydrogen anymore, I want moles of ammonia. So what ratio am I going to use? Well, to get rid of hydrogen, it needs to be in my denominator. There's one in my denominator. And this one I actually didn't flip. But I need to get 2 moles of ammonia. So this is what I want to use, except for I want to flip it. Forgot to flip it in the beginning. So I'm going to put my 3 moles of hydrogen in the bottom and my 2 moles of ammonia on top. So my ratio for my balanced chemical equation is for every 3 moles of hydrogen, how many moles of ammonia do I produce? 2. So my moles of hydrogen on top and bottom will cancel. So I'll just make 0.2 moles of ammonia. Okay? We're going to have you try number 3 all by your own. I will help you balance the chemical equation, but this is something you should be able to do by now. It says translate the following equation. Potassium chlorate undergoes a decomposition reaction to form potassium chloride and oxygen gas. So remember, potassium's +1 in the first column. Chlorate's -1, it's a polyatomic ion. Potassium's +1, chlorine's -1, and oxygen's a diatomic. So KClO3 gives you KCl plus that diatomic oxygen. So right now, looking at it, I can't move on to stoichiometry until I've balanced my chemical equation. So what I'm going to do is balance my oxygens first. I have 3 oxygens on the left and 2 on the right. A number that both of them can go into would be 6. Now I have 2 potassiums and 2 chlorines. I can quickly fix that by putting in for potassium chloride. So then it says, how many moles of oxygen can be produced by letting 1.2 moles of potassium chloride react? So we're asking how many moles of oxygen when you give us 1.2 moles of potassium chlorate. So start by writing 1.2 moles of potassium chlorate. And without writing all the different molar ratios, let's try to write one from scratch. So, according to my balanced chemical equation, for every 2 moles of potassium chlorate that I have, I'm going to make 3 moles of oxygen. So my goal is to get to moles of oxygen, so that's going to go in my numerator. So 3 moles of oxygen go up here from my balanced chemical equation. To get rid of moles of potassium chlorate, I need to put it in my denominator. So for my balanced chemical equation, that's 2 moles of potassium chlorate. So now my units of moles of potassium chlorate are going to cancel. And the units I'm left with are moles of oxygen. This is why you have to put all of your units into your expression. You need to make sure that the math that you did justifies the question that you're solving. So 1.2 times 3 divided by 2 is 1.8. You're going to make 1.8 moles of oxygen. I don't know why that changed color on me, but it did. Okay? The next 2 things I think you can solve, because it's just dimensional analysis from the previous unit, which you just took a test on. I will put up the key really quick, and then I want you to solve the next one on your own. Okay, here are my answers for the next 2 questions. Hopefully you were able to do that from the last unit. Let's do one more page. Okay, it says how many moles potassium chloride? Oh, so we're using the same question. It's continuing. So KClO3 makes potassium chloride plus oxygen gas, and then we balanced it. How many moles of potassium chloride, so this is what I'm looking for, can be produced by letting 1.2 moles of potassium chlorate react? So again, they're giving us this 1.2 moles of potassium chlorate. And this time, it wants to know how many moles of potassium chloride. So according to our balanced chemical equation, for every 2 moles of potassium chlorate, I'm going to get 2 moles of potassium chloride. So I put my units of moles of potassium chlorate in my denominator, so they cancel, and I will get my units of moles of potassium chloride in my numerator. And look at that, it's the same answer. We call this a 1-to-1 molar ratio. If they have the same coefficients out in front, they're probably going to have the same amount of moles in a chemical reaction, as long as there's nothing called a limiting reactant. So the next 2 parts you can do on your own. This is from the last unit. And then tomorrow we will do mass-to-mass stoichiometry. You're going to work on section 1 of your homework tonight in class, work together and make sure you understand the concepts. And then we are going to continue mass-to-mass stoichiometry tomorrow. But first I want you to solve these 2 questions, pause the video, and then pop it back up when you've solved them to check your work. Okay, there's my work. Just make sure your units cancel out top and bottom. Again, to go from moles to grams, you need molar mass. So this is the molar mass of potassium and chloride from your periodic table. And then go from moles to molecules, you have to use Avogadro's number. So that's 6.02 times 10 to the 23rd. So again, start your homework today in class, work together, and then tomorrow we are going to do mass-to-mass stoichiometry.